This is Chapter 6, Ionic and Molecular Compounds. Today we're starting Section 6.5, Molecular Compounds and the Sharing of Electrons. We just spent several sections talking about ionic compounds and how a metal and a nonmetal will transfer electrons between them in order to satisfy the octet rule and then combine together into an ionic compound. The atoms in a covalent or a molecular compound are also trying to interact with one another in a way that gives them a full octet, but they don't do it by transferring electrons, they do it by sharing electrons between them. This sharing causes the molecular compounds to have different properties than the ionic compounds, and it also results in a wide variety of different compounds that can be formed from two given elements. So, for example, if you have sodium and oxygen, that's a metal and a nonmetal, and they can really only form one kind of ionic compound because of the charge balance between them. But if you have carbon and oxygen, those are both nonmetals, and so they can share electrons in multiple different ways. And so you can have one carbon sharing electrons with two oxygens, and that's carbon dioxide, or you can have one carbon sharing electrons with just one oxygen atom, and that's carbon monoxide. So you can form multiple different compounds from the same two elements. Okay? So there's a lot more variety in molecular compounds. In these slides, what we're going to be learning is how to interpret the formula of a molecular compound and how to write the formula name or the compound name from the formula. Again, molecular compounds form when two or more nonmetals share electrons between them. And these shared electrons are what constitute the covalent bond. It's called covalent because the electrons that are shared come from the valence shell of both atoms, right? So they're covalent. And these valence electrons are shared because the atoms are trying to achieve more stability. Okay? They're still following the octet rule where an atom is more stable if it has a full 8 electrons in its outermost valence shell energy level, where the S and the P sublevels are both filled with 8 electrons. Okay? A molecule, by the way, is a discrete group of atoms in a definite proportion. So unlike most ionic compounds where you just have a simple ratio between a large number of positive ions and a large number of negative ions, here you actually have discrete individual units of atoms bonded to one another that form sort of new particles with new properties. In the formula of a molecular compound, you'll typically see the symbols for two nonmetal elements written. And after each symbol, you'll have a subscript number indicating the number of that type of atom in the molecule. If there's no number given, then you assume that there's only one of those atoms in the molecule. So for example, with CO2, you have two oxygen atoms and only one carbon atom. Okay. Typically, the least electronegative element is written first. So in this case, oxygen is more electronegative than carbon, so carbon goes first, which is sort of similar to ionic compounds where the metal goes first, because the metal is always going to be less electronegative than a nonmetal. That's part of the definition of what it means. So the one with the highest metallic character goes first. Even though we're only dealing with nonmetals in molecular or covalent compounds, you can still talk about some being sort of more metallic than others, or at least less electronegative than others. So in all of these cases, the least electronegative element is first. So nitrogen is less electronegative than oxygen for these two, and oxygen is less electronegative than fluorine. Fluorine is the most electronegative element. Okay? So these examples also show us how you can form multiple compounds, again, from two of the same elements. So nitrogen and oxygen don't come together just to form one type of compound. They form several different compounds. These are only two of them, but there's many other compounds that can be formed from nitrogen and oxygen. In the name of a molecular or covalent compound, you'll see the names of the two nonmetals written in the same order that they appear in the formula. So the least electronegative element name will appear first, and then the more electronegative will appear second. And just like in an ionic compound name, the second element given has the ending changed to IDE. So you just keep the first syllable of the element and you change the ending to IDE. So just like with ionic compounds where you have oxide and fluoride and sulfide, that carries over to covalent compounds as well. Okay, so NO2, for instance, is nitrogen dioxide. Okay, it's not dioxygen or something like that, it's dioxide. And then you'll notice that I also mentioned a prefix, the di in front of the dioxide. That prefix indicates the number of that atom. Okay, so the prefix corresponds to the subscripts in the formula. The prefix in the name corresponds to the subscript in the formula. Okay, and the prefixes are these prefixes given in this table here, table 6.10. For 1 is mono, then 2 is di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And that should be all you need to know. So again, several compounds can be formed from the same two nonmetals. So with carbon and oxygen, you can form carbon dioxide, where you see the prefix di to indicate that there are two oxygens, or you could have carbon monoxide to indicate that there's really only one oxygen. There's no subscript after the oxygen, so you assume that it's one. Now you'll notice the mono prefix, you might think that there's a mono in front, right? So these could be monocarbon dioxide and monocarbon monoxide. But typically, if it's the first element that there's only one of, you leave out the mono. Okay, so oftentimes the mono will be dropped from the first element in the name. Usually that's the case. And another thing to notice, just sort of the language of this, when the vowels O and O or A and O appear together, the first vowel is omitted. So here, mono ends in an O, and then oxide begins in an O, right? But they don't say mono-oxide, and they don't write two O's, you just say monoxide, so they sort of get blended together. Okay, so that's what happens down here for nitrogen monoxide. It also happens with the A and the O, so if you have hexa, hepta, penta, tetra, things like that. Tetraoxide would actually just be tetroxide. Heptaoxide would be heptoxide, and so on. Here's a table of some common covalent or molecular compounds. It has their formulas, their names, and some commercial uses. You don't have to worry about memorizing the uses. But it might help you to familiarize yourself with the formulas and the corresponding names for some of these, because these are, again, common compounds that you'll see over and over again in this class. There'll be a lot of examples that we do throughout this chapter and the rest of the course that we use many of these compounds. Obviously others as well, but this is a good starting place, and it can help you to review, right? If you can look at the formula in the first column and figure out the correct name in the second column, that's a good way to test yourself. There's a couple of things here to look out for, which is, for instance, in NO, you have one nitrogen and one oxygen, so they suppress the mono in front of nitrogen, which is usual, but they also drop the mono from in front of the oxide. So you could call this nitrogen monoxide, but technically it is nitrogen oxide, okay? And N2O is dinitrogen oxide. So if you wrote nitrogen monoxide, it wouldn't technically be wrong. People would still understand what you're talking about, but it's not really the accepted name for these. So if we're given the formula of a compound, how do we name it? Okay, say we're given this formula, NCl3. Okay, one thing I want to mention before we go any further is Cl is chlorine. Okay, get used to seeing chlorine. Because you're going to see it a lot, and sometimes if you see a formula like this, people interpret it as NCI3, because N is nitrogen, C is carbon, and I could be iodine, right? But that's not really what we're going for here, so don't get tripped up by the font choices or the style choices. The Cl3 is 3 chlorine atoms, okay? It's not a carbon and 3 iodine atoms. We're not really going to see iodine too much in this class, so it's pretty safe to assume that if you see this, then it's Cl for chlorine, okay? So the first thing we have to do to analyze this problem is to figure out what elements these are, right? And I gave you the first one, or really the second one, which is chlorine. The first nonmetal is N, okay, which is nitrogen. So you just look on a periodic table if you're not familiar with the symbols yet, and you find N, and it'll tell you that it is nitrogen. And then, of course, you look up the second symbol in the formula, Cl, and you find that it's chlorine. But for the second element, the second nonmetal in the formula, you just take the first syllable of the element name and you change the ending to IDE. So instead of chlorine, this becomes chloride. Okay? So far we have nitrogen and chloride. But we can't stop there, because there may be multiple ways that nitrogen and chloride can combine together to form compounds. So the next thing that we need to do is add prefixes to the element names. Okay? Since there's just one nitrogen atom, you could say mononitrogen, but since it's the first one, we're going to drop the mono, so you don't really need the prefix for that. And then there are 3 chlorine atoms, and so the subscript 3 means there's 3 chlorine atoms, and that corresponds to the prefix tri, right? Like a tricycle has 3 wheels. So the name of this compound, NCl3, is nitrogen trichloride, meaning nitrogen and 3 chlorines. Let's try another example. Now we want to give the name for the molecular compound with the formula B2O3. B2O3. And so we can analyze this the same way. We have a chemical formula with 2 elements. They're both nonmetals, so we can be sure that it's a molecular or covalent compound. It's always a good idea to check that ahead of time to make sure you're following the correct rules. And in the formula, the first element given is B for boron. Okay? If you're not familiar with that symbol yet, just consult the periodic table for now, and that's fine. The second element is O, which stands for oxygen. You should definitely know that one by now. We're going to use that all the time. But instead of just calling it oxygen, because it's the second element, we have to change the ending and make it into oxide. Okay, so far this compound is boron oxide. But there may be multiple ways that these can combine together, so we want to add prefixes to those words to indicate these numbers here, the number of atoms in the molecule. So again, B2O3 means that you have 2 borons. The subscript 2 means there are 2 boron atoms in this molecule, and that refers to the prefix di. Okay? The 3 after the O means that there are 3 oxygen atoms in the molecule, and that corresponds to the prefix tri. So when you add those prefixes, you get diboron trioxide. 2 borons, 3 oxygen. Diboron trioxide. You can see the prefixes here are highlighted in red just to make it clear for you. Obviously the name that doesn't matter for the name. Well, what if we want to go the other way? Maybe we know the name of a compound and we want to try and figure out what the formula is. Okay? In ionic compounds, that required some charge balancing. Here, we actually don't have to do that. It's even a little bit simpler. Because the prefixes tell you how many of the atoms there are, you can just look at the prefixes to figure out the formula. So here the question is, write the molecular formula for diphosphorus pentoxide. Diphosphorus pentoxide. And so you can just analyze this by looking at the names, right? You have to be able to recognize which are the prefixes and which are the element names, okay? So the di is a prefix, the pent is a prefix. The element names are phosphorus and oxide, okay? So we write the symbols for those elements. Phosphorus is P, oxide comes from oxygen, which is O, okay? So this is where we get phosphorus and oxygen from, P and O, I should say. And then the prefixes just become subscripts. This prefix di means 2, and the prefix penta, like a pentagon, means 5. Okay? So what this means is that we have 2 phosphoruses and 5 oxygens in this molecule. And so we can write the formula as P2O5. Okay? Make sure that those numbers are subscripts. They're smaller and lowered below the baseline of the letters that you're writing. In the real world, if you're trying to translate a compound name into a formula, or vice versa, you might not know right away whether the compound is ionic or covalent. But it is important for you to figure that out because the rules that you use to translate the name into the formula, and vice versa, depend on whether it's ionic or covalent. They're different for ionic and covalent compounds. So the first thing you always have to do is figure out which one you're dealing with. In this class, it's pretty simple. We keep away from any curveballs or anything like that. So basically, if the compound name or formula starts with a metal, then you're definitely dealing with an ionic compound. Okay? If you see a metal in the formula, it's definitely ionic. The other possibility, the only way that you could have an ionic compound without a metal is if you have this NH4 plus ion instead. Okay, the metal would be the positive ion in an ionic compound. So this is the only polyatomic positive ion that we deal with in this course that could take the place of a metal. Okay, so either a metal or NH4 plus. Those are the only two choices for the beginning of an ionic compound, the first part of the name or the formula. Okay, so K2O, K is potassium, that's a metal, so it's definitely ionic. If the first element in the formula or in the name is a nonmetal, well, then you're probably dealing with a covalent or molecular compound. Okay, you just have to make sure it's not this one exception with NH4, right? So you could say NH4 Cl, for example. This is a compound, this is a formula, and it starts with a nonmetal technically because it starts with an N, but really it starts with NH4, which is ammonium, and that's an ion. So NH4Cl is an ionic compound. Okay, so as long as you're aware of the exception with ammonia, then if it begins with a metal, it's ionic. If it begins with a nonmetal, it's covalent. And that's really all you need to know. Now that we know how to name both ionic and covalent compounds, we can construct a flowchart or a decision tree like this to help us figure out the names from the formulas. So I don't expect you to have this entire chart memorized in your head at all times, but it can help if you're stuck or if you're starting out to see how the different things affect the name, the different properties of the elements involved affect the name. Okay, so to do an example, we're talking about covalent compounds. So let's take a compound that I know will be covalent, but the decision tree or chart will help us to see that as well. So the formula will be PCl3. Okay. So when we look at this formula, we go here to the first box, and it asks, is the first element a metal or ammonium, right? Or is it a nonmetal? Okay, so the distinction is between a metal and ammonium on one hand, or a nonmetal on the other hand. Okay, so this is definitely not begin with ammonium, it begins with P, and P is phosphorus, which is a nonmetal. So we're going to be going on the right-hand branch of this chart. We're going to be going this way, okay, to the nonmetal, and that takes us here, which reminds us or shows us that this is a molecular or covalent compound. Since it begins with a nonmetal, it's going to be formed from two nonmetals, and it's a molecular compound. And so now we need to look at both of these branches, okay, because we have both the first nonmetal and the second nonmetal. The first nonmetal, we use the whole name. So P is phosphorus. So it's going to stay phosphorus. You don't change the ending. And you would add a prefix to indicate the subscript in the formula. But since there's no subscript, you assume that there's just one of them. And you could say that the prefix is mono, but again, we drop the mono on the first element name. Okay, so instead of saying monophosphorus, you would just say phosphorus here, since phosphorus is the first element in the formula. For chlorine, right, Cl3, chlorine, we use the first syllable of the nonmetal, which is chlor, and end it with ide, so it becomes chloride. Okay, you should be familiar with this from the ionic names. So chloride does get a prefix. Okay, there's Cl3 means there's 3 of these chlorine atoms, and so we need a prefix that means 3, and the prefix that means 3 is tri. So chloride becomes trichloride, right? And then the last thing to do is just put these together. You have phosphorus and you have trichloride. So the name is phosphorus trichloride. You would write it with a space in between as 2 separate words, but the tri is attached directly to chloride. Phosphorus trichloride. So here we have a few different example problems. Okay, you're given the formulas and you're expected to pick the correct compound name. So SiCl4 is this ionic or covalent? That should be the first thing that you ask yourself. Okay, Si is a nonmetal, so this is covalent. Okay, this P is phosphorus, that's a nonmetal, so that's covalent. Here we have Cl, that's a nonmetal, so this is covalent. So since we're in the covalent chapter, all these are covalent. But again, it's a check that you should do before you start thinking about the name, because you always have to make sure you're following the right rules. Okay, so SiCl4. Si is silicon. You can look it up in the periodic table. There's just one silicon atom in this compound. Because there's no prefix following the Si, that means there's only one of them. So it should be silicon. You might say it's monosilicon, but again, that mono gets dropped from the first element, and none of these choices have mono in front anyway. So it's not tetrasilicon because there is not 4 silicons, right? There's only one silicon. The Cl is chlorine, and there are 4 of those. Okay, so the 4 after Cl means there are 4 chlorines. So chlorine becomes chloride, and since there's 4 of them, it should really be tetrachloride. Okay, so C is the correct answer here. Silicon tetrachloride. The tetra means that there are 4 chlorines. In the second problem, we have P2O5. Okay, P is phosphorus, O is oxygen. Oxygen becomes oxide. Okay, P2 means there are 2 phosphoruses, and so the prefix for 2 is di, so it should be diphosphorus. And the prefix for 5 is penta, so it should be pentaoxide, which you'd blend into pentoxide. So here the answer is C again, diphosphorus, pentoxide. And then in the last one, you have Cl2O7. Okay? In this case, the Cl2 means that you have 2 chlorines, and the O7 means you have 7 oxygens. So 2 chlorines is dichlorine, and 7 oxygens is heptaoxide or heptoxide. So the answer here is A, dichlorine, di for the 2, and hepta for the 7. Okay, and then chlorine and oxide. Now, there's one interesting thing here to note, which is that in this compound, the Cl stays chlorine, whereas in this compound, the Cl becomes chloride. Okay, or I should say chloride down here. Okay, the correct name. So the reason for that is, again, in the first compound, Cl comes second. It's more electronegative than silicon, so it comes second and it gets changed to the IDE ending because it's second. In the third problem, chlorine is actually less electronegative than oxygen, and so it comes first in the formula, and since it comes first, you don't change the ending, and it stays as chlorine. Okay? So you have to be careful about this. There are certain exceptions, well, not exceptions, but there are certain manifestations of this rule that are a little strange at first, so you have to keep an eye out. Here we have a few more example problems, but these are mixtures of both ionic and covalent compounds, and so we need to figure out what kind of compound it is before we know which set of rules to apply to figure out the correct name. So for these, I'm going to go through first to show whether they're ionic or covalent, and then we'll go through naming them. Okay, so the way to figure it out is always the same. You look at the first element. So for A, the first problem, the formula is SO3. S is the first element. S is sulfur, and that's a nonmetal. So this is definitely a covalent compound. Okay. For B, the second problem, the formula is BaCl2. And so the first element is Ba. Ba stands for barium, which is on the left side of the periodic table. It's a metal, and so this is definitely an ionic compound. In C, the formula is NH4,3PO3. So it's a little confusing to say it because there's parentheses involved. When you look at the formula, you might be confused as well because it starts with N, nitrogen, which is a nonmetal. So you could maybe think that it's a covalent compound for a second, but you have to be able to recognize that that N is really part of this NH4 unit here, and that NH4 is the ammonium ion. Okay, that's the one exception where a compound might not begin with a metal and still be ionic. So this is an ionic compound because it involves the ammonium ion. For D, the fourth problem, the fourth formula is Cu2CO3. Okay, so the first element is Cu. That stands for copper. Copper is obviously a metal, and so this is also ionic. Okay, and then the last formula, E, the formula is N2O4. Okay, N2O4. The first element is N. This N is not part of ammonium, it's just N. And so that's nitrogen, which is a nonmetal, and that makes this definitely covalent. Okay. And now that we know what types of compounds these are, we can go through and name them. Okay. Naming the covalent compounds is the easiest, so I'm going to start with that. So for SO3, you have 1 sulfur and 3 oxygens. So 1 sulfur, you could say it's monosulfur, but again, you drop the mono from the first element, so it just becomes sulfur. And then oxygen becomes oxide, but there's 3 of them, and you need a prefix, so it's trioxide. Okay, sulfur trioxide. For E, the last one, which is the other covalent compound, the formula is N2O4. Okay, so you have nitrogen, but there's two of those. You can't just drop that two. So this is going to be dinitrogen. Okay, and then O is oxygen, which becomes oxide, and you have four of them. The prefix for 4 is tetra, but tetraoxide becomes tetroxide. Okay, so dinitrogen tetroxide. Now we can go back and do the ionic problems. For B, the formula is BaCl2. So barium is a main group element, a main group metal. So it always has a +2 charge. We don't have to worry about a Roman numeral or anything like that, so it's just barium. The Cl becomes chloride. So this is barium chloride. Remember, there's no prefixes in an ionic compound. Just because there's a 2 here doesn't mean that you should call this dichloride. Barium chloride is sufficient to indicate the formula here, because you can rely on charge balance to figure out how many of each you have. For C, remember we said that NH4 is ammonium, so that's going to be the first part of the compound name. There are 3 ammoniums in this formula, right? That 3 here outside the parentheses means that you have 3 separate ammonium ions, but we don't care about that for the name, right? It's not triammonium because it's an ionic compound. We don't use prefixes, so it's just ammonium. And then this, which is another polyatomic ion, which is phosphite. PO3 is phosphite. So this is ammonium phosphite. Okay, you really need to know your polyatomic ions to name these. D, the last one, you have Cu, which again is copper. But if you look on the periodic table, you should look in the periodic table to see where copper is, and you'll see that it's a transition metal. Okay, it means it has a variable charge, and we're going to need to write a Roman numeral to indicate the charge. Okay, the other ion, the anion in this is CO3, which again is a polyatomic ion. That is carbonate. Okay, carbonate is the name, but CO3 as an ion has a -2 charge. Okay, so in this formula you have 2 copper ions, because it's Cu2, and 1 carbonate ion. So the 2 copper ions balance the -2 charge from the carbonate, which means they each have a +1 charge. So the copper in Cu2CO3 has a +1 charge, which means the Roman numeral is just going to be the Roman numeral 1. So this is copper 1 carbonate.